or a melting point. So to increase melting point, it generally increases. Here is going to be the increase symbol. It generally increases to the top of the periodic table, so up the period, and to the right, across the groups, group-wise. Now, why is this the case? Well, as we go towards the right, there's going to be an increased number of electrons. If there is increased number of these electrons, there's going to be more interaction with protons in the electron sea. I'll illustrate what that means shortly. But let's first iterate here. To the right means more unpaired electrons equals more electrons in the sea. Electron sea. This thereby means it equals more positively charged ions. To interact with. And if there's more positively charged ions to interact with, this will therefore increase the strength of metallic bonding. And therefore, lastly, it increases this interaction. So maybe here I'll write increase of interaction, more interaction. And thereby this equals higher melting point. Or maybe I'll put here an increase in melting point. Now let me show you what this electron sea is. If we look here in the 3D orbital, I'm going to have to do it in green. So here we have in the 3Ds, because obviously this is 4s2. Okay, so this is obviously 4s2. So here would be the 3Ds. So if we have, let's say, 2 electrons here, these 2 electrons are going to want to leave this orbital because there's nothing really to do there. It would rather leave and interact. So these are the electrons now. It would rather interact with any of the protons in the electron sea. So everything here would be the electron sea. And it's going to interact with them. So the more interaction it does out here in the electron sea, it's going to increase the strength of metallic bonding and therefore increases the melting point. So the more electrons, so these unpaired electrons, the more of them that are here, the higher the melting point. Now let's take that same example with a 3D orbital. You notice that we have, let's say, 2 electrons here. Again, we're in the 3D, so we're starting here. So this would be our first electron that we see over here, and this here will be our second electrons for the titanium. So here, again, third group, this here, the fourth, this here, the fifth, this here, the sixth, this here, the seventh, okay, and then 8, 9, 10, etc. So let's start with maybe the 2 electrons, so this one and this one over here. So we are in group 4 right now. So we are dealing with titanium and zirconium. So where is that? We have titanium here and zirconium here. So this is where we are at. Notice how it's very, very far down. But as we increase more and more electrons, it's going to continue to increase. So let's go to the 5th one. So if we add that next electron, now we are no longer with the titanium and the zirconium. Now we're in the vanadium and the niobium. So where is that? The vanadium over here, the niobium, okay, or even the tantalum, right? Tantalum's up here, okay? You see how it is a ginormous, huge, steep slope. Okay? Because this makes sense. The more electrons that you have in this C, this is going to be attracted to more cations. Where it gets a little bit different now is where we add that last electron. So now this electron here, we're now dealing with, let's say, chromium or molybdenum or tungsten. That next electron here, now it needs to think, would it join the electron C and continue to increase that melting point, or would it stay? Would it stay right over here so that it can wait for that last electron in order to be happy? Well, unlike the Bohr diagram, what you've learned in previous grades, it's not going to stay. It's actually going to join. It's going to join into that electron C. But even though it does that, it is still obviously going to increase the melting point, but it's in a tight spot. So as you can tell, the steepness of this slope has decreased because it doesn't necessarily want to. It is wanting to get that electron in, but it still joins its friends to want to interact with the electron C. So the steepness has decreased, but it's still going up. So it's still interacting with the protons or any other ions that are in play in the electron C. Once we get that last electron in, this is where it is a complete cutoff. We were, again, at, where were we? We were at tungsten and molybdenum and chromium, right? Because we had 4, right? 1, 2, 3, 4. We had 4. Okay, so we were here in group 6. But once you add that last electron, we are now on the 7th. And as you can see, our manganese, technetium, and rhenium, you see how it all goes down. It crashes downwards. Crashed, crashed, crashed. Now, why is this the case? I mean, it's quite obvious. Once you have that last electron, all of these are half filled. This is quite stable. Obviously, it would be better if we had all of them fully filled, the positive and negative spins all filled within each orbital. But this here is still quite stable. So it definitely does not want to do that. It's not going to continue contributing more electrons in this electron C. So these unpaired electrons are not going to do that. They're going to stay kind of where they are. So these elements here, manganese, technetium, and then the rhenium, they're going to stay where they are, and hence the melting point drops drastically, as showcased over here. Now I'm going to do it a different color here. Once I get, let's say, an electron over here, it's now going to start to increase again. Because this electron here is now, if it wants to interact in that electron C, it's going to increase that melting point again. So as you can see, it's slowly starting to increase up the graph. Slowly starting to go back up. And then, of course, you start adding, however, more electrons, though. Just like the previous example, the more electrons you start adding, the less likely it wants to be there. It does not want to be in this electron C. It would rather stay where it is because it's approaching and slowly getting closer towards this full orbital that is going to have all paired electrons in. So it gradually gets lower and lower and lower the more electrons you add in. Because the difference was before you only had one unpaired positive spin on the orbitals. Now you have 2. So once this gets 2, we're very, very stable. Once you start getting this, it's also very stable. Once you start getting this, it's also very stable. So this was different than the last example. The last example, you had only one positive spin. Now you have a positive and a negative spin. So as you continue to go down, as you continue to go to the right, the more you're adding, the more you're pairing, the more comfortable it is in this state. So why the heck would it want to participate in the electron C? It wouldn't. So as soon as you add that last one over here, this would be group 12, so this would be 8, This would be 9, this would be 10, this would be 11, this would be 12. Once you hit that zinc or the cadmium and then the mercury, it is now top-notch, very, very stable. So that would be kind of like down here. It would be a very, very, very low melting point. Okay? So that's that first part. Now we're going to have a look at a chart and introduce the concepts of polarizing power and how polarized an anion can be, and look at the trends of the melting point in practice. Then I'll give you some review questions, and then we'll be good. So let's have a look at polarizing power. And polarizing power just means it's the ion's ability to pull the electron density towards it within an ionic bond. So ion's ability, so think about it as its strength. It's ion's ability to pull electrons, densities, towards it. And this is going to be the perspective of the cation. So for the cation, the higher the charge is going to equal more polarizing power. So if for short, I'm just going to put pole power, so more pole power. And not only higher charge, but we also need to look at its size, its atomic radii. So if we have a smaller radii, again, this should be quite obvious to you now, where the atomic radii size is incorporated within the periodic table. So it's obviously towards to the top and to the right. So the smaller the radii, so around this area here, this is also more polarizing power as well. Now, if we look at polarizability, this is in the perspective of the anion. And the polarizability is just the tendency to be polarized. So if we look at from an anion's perspective, similarly with a charge, if there is a higher charge, there is more polarizability. However, in contrast to the cation, if it's a larger radii, this one's going to be more polarizability. So I'm just going to put a little disclaimer down here for polarizability. If there is more polarizability and more polarizing power, this is going to increase covalent character, which you should know is already just the opposite of the ionic character. So the more ionic it is. So more polarizing power, more polarizability means it is more covalent, a higher covalent character. More polarizing power and more polarizability. What does it equal? It equals more covalent. An increase, here I'll just write it as an increase in covalent character. And obviously it is true, opposite is true for vice versa. So let's look at a few examples. I also want to illustrate where the polarizing power would be. So the higher up towards the left, up here, and near the top, it has high polarizing power for the cation, so up here, but it would have even more polarizing power if it was more towards the right. So beryllium here would have more polarizing power than, let's say, lithium, because we're going towards the right. There is going to be more charge because beryllium has a 2+, the lithium only has a 1+. Okay? Or something like a sodium or a magnesium. Okay, the magnesium has more polarizing power. Same thing with this aluminum. This aluminum has more polarizing power than magnesium because of its charge of a 3 plus. And all of these here are very, very high up. So again, the higher up it is, the more polarizing power because it's smaller. The larger it is, it's going to be down here, let's say like cesium or something like barium. It's going to have a larger radii because of the shielding effect. So the higher up you go and higher up to the right you go, the more polarizing power. So more polarizing power would be like here, polarizing power, increase in polarizing power. Okay, so we can have that over here. Polarizability, it's going to be a little bit different. Higher the charge, more polarizability, so more towards the left. But larger radii means more downwards. So something like arsenic here would have more polarizability than, let's say, selenium, because arsenic has a higher charge than the selenium, right? The 3 minus as opposed to the 2 minus. Same thing with the phosphorus or the sulfur. The sulfur has more polarizability than the sulfur. Charge increases that way. What we should know before we look at the example is the lower the polarizing power and the lower the polarizability, the more strongly held they are, and it's going to increase the melting point. It's just the exact opposite of what we looked at here. More polarizing power, more polarizability, more covalent. So it's going to be weak. But if we have less polarizing power and less polarizability, this is going to increase the ionic character. So it's going to be a lot stronger held together, and then it's going to be harder to break apart, which is going to be a higher melting point. So let's look at a few examples here. If we look at cesium bromide, and we look at sodium iodide, we look at cesium right over here. So not very high polarizing power. You can already tell. Its charge is very low because it's on group 1, so it's only a 1 plus. And it's very low on this periodic table, which means it has low polarizing power. So it's quite low, the cesium. But who is it paired with? It's paired with a bromine. The bromine doesn't necessarily have a strong polarizability either. Okay, it's kind of near the bottom, but it's also near the top. It's kind of in the middle. Let's compare that with, let's say, NaI. Sodium is up here, higher polarizability, so higher polarizing power over here. And the iodine, though, high polarizability. And both of these examples are within the same range. Cesium to bromine is kind of here. And you can just kind of visually look at it. And then the Na and then the I, it's kind of here. They're kind of in the same area in retrospect. So which one is going to be stronger? It's going to be the NaI, just because NaI here, there's a bigger margin between this Na and then this iodine versus the cesium and then the bromine. They're all in different quarters of this of their domain. But sodium, it's just a little bit higher. Just visually you can tell. It's a little bit higher in terms of one more period, so it's going to be a bigger margin. So that bigger margin is going to increase that strength together. Hence why the NaI here has a little bit higher melting point than the cesium bromide. So 661 versus the 636. But if we want to get into a more clear-cut example, let's have a look at these two, MgCl and NaCl. So let's look at MgCl, and then let's look at NaCl. Where is our Mg? So our Mg here is right over there. And where is our Cl? It's right over here. So I'll do it in a different color. So Mg here, Cl here, and then our sodium right over there, also paired with the chlorine. we want to get the least amount of polarizability with the least amount of polarizing power. That's going to tell which one is going to be stronger. And as you can already tell in the chart, the further down you go, the stronger it is. So we can already tell that our NaCl is going to be stronger. It's going to have a higher structure being bonded together. But let's look at why. Our Cl is over here. That's not changing. The only thing that's changing is going to be our sodium and our magnesium. Our magnesium is over here. Our sodium is over here. Which one has less polarizing power? I know it's very discrete, but it is the sodium because it's a little bit more on the left-hand side because it has less polarizing power. Na here has a smaller charge. So because that, again, that margin is getting wider now between the sodium and then the chlorine as opposed to the magnesium and the chlorine, we can tell that the Na here is going to be greater than the MgCl. So you see an 801 versus a 714. Hopefully this is starting to make sense. So we're trying to look at the smaller polarizing power and the smaller the polarizability. Now let's look at MgF and MgO. If we look at MgF, Mg is right over here. Now the Mg is not going to be changing, but we're looking at the F and then the O. Now right here at first we are looking at an exception. Because chemistry is just full of exceptions. If we look at the margin difference, this here not changing, quite low polarizing power. But here, the oxygen and then this fluorine, it's farther away. So this one here is lower polarizability than the oxygen. So if this one is lower polarizability, the fluorine, and that's with the magnesium, the MgF should be stronger, more ionic character, because this is lesser and the F is lesser than the O. So the F and then the Mg should be together. But as you can see here, the MgO is stronger. Why? It has to come down to the charge. Because this Mg had a 2+ charge and then this F had a 1- charge, there is a charge imbalance. This Mg has a stronger charge than this one, as opposed to the MgO, which has a 2+ versus a 2-. So because they're the same, this is an exception rule where if their charges are large and they're both the same on each ion, it takes precedence. So MgO is actually going to be stronger held together than the MgF. And this is not minute. It's quite large, 2825 versus 1263. So I just want you to take this with a grain of salt. Do not just look at polarizing power. Do not just look for, the more polarizing power, the more polarizability, and it's obviously going to be the more covalent. This is in general when you're looking at the charge versus the radii, but it's not always going to be like that because there's other factors in play as well, like we just looked at, charges being the same. And it's a bigger bonus if the charges are larger. So let's say like a 3+ and a 3-, or like a 2+ and a 2-. And if they're the same for the both ions, that takes much more precedence over this polarizability and polarizing power rule. So it's very important that you take this, please, with a grain of salt. Now let's look at a few review questions for you to try together. Now let's look at magnesium fluoride and aluminum fluoride. Magnesium fluoride, aluminum fluoride. So 3 is down here, 2 is down here. So let's have a look at their melting points. Magnesium fluoride, right over here, or we'll do it in green, so Mg is over here, F is over here. So Mg and then F versus Al and then F. So where is Al? It's over here. We have to look at which one is going to be stronger. Which one do you think would be stronger? If you want to pause it for a sec, you can give it a try. The answer is going to be the ALF, the ALF3. So again, the F's here are the constant. But we have to now start looking at the charges. Which charge is going to be greater? The charge for the Al is going to be greater than the Mg. So because Al is greater than the Mg, this here is going to be stronger. It's going to have a higher melting point. Now here are your review questions that I want you to give a try. Please pause the video. And as you try this, try to be as detailed as possible with your response, and then unpause it and then be able to see the answer. I will go through the answers with you together. So again, pause the video and give this a try on your own. All right, let's have a look at which one is more covalently charactered. So a higher covalent. Not ionic, we've been focusing on the ionics, but let's look at which one's more covalent. Let's look at the Mg here versus sodium chloride. So the Mg here, 2+ charge, whereas the Na has a 1+ charge. They're in the same period, but this one has a higher charge, so this is going to be more polarizing power in terms of polarizing power. Then we look at the iodine and then the chlorine. Which one has more polarizing power? Iodine also has more polarizing power if you were to look at it on your periodic table. So our iodine here is greater than the chlorine in terms of polarizability. Polarizability. So it's quite obvious right now that the Mg and the I, they both clock in with a higher polarizing power and higher polarizability respectively. So this here for sure is more covalently charactered. So therefore, more covalently charactered is the MgI2. So it's going to have a lower melting point than the NaCl. What factors affect the way in which ions pack as they form crystals? Well, we did look at the different types of attraction because we looked at some exceptions with the charges being greater but also being of the same magnitude for the ion and for the cation and the anion. And obviously what's more obvious is the radii. And of course, the charges. So all of these are factors to consider when they pack to form crystals. And then lastly, let's look at number 3. Potassium fluoride. Fluoride is a water-soluble ionic compound. This would obviously have to be a solid here. Describe in general what characteristics you would expect to see for each of the following properties of the potassium fluoride. Well, we'll have a look at the melting and boiling point. This is obviously an ionic compound, so it's going to have a high melting point. High melting and boiling point. The more covalent it is, the easier it is to break apart. Because this is ionic, it's going to be more difficult to break apart. Hardness, it's obviously going to be hard, and it's going to be quite brittle. It's not as if we have a metallic bond going on. This is a crystal lattice, so it's going to be quite brittle. It's going to be quite hard. Malleability, not malleable. Again, we are dealing with a lattice structure that does not move. Next, conductivity in aqueous solutions. When the hydrogen bonds are strong enough to break these, to overcome these, you're going to start getting the K1 plus and the F1 minuses. And then electrons will be able to transfer their kinetic charges to neighboring electrons, and this is where conductivity occurs. So, is it conductive in an aqueous solution? Absolutely. So yes, it is conductive. However, conductivity in the solid state, no, this is not going to be conductive. Because, like we've always looked at today, ionic bonds are very, very strong. So the electrons are going to be very polarized into one ion over the other. And because of a crystal lattice structure, the electrons cannot move around freely. In a metallic bond, they can, but in an ionic bond, they cannot. So it will not be able to be conductive unless we break it apart. The only way we can do that is in a molten state with lots of temperature, lots of pressure, or with water, a very, very strong universal solvent that is able to break them apart. Once they are broken apart, we go back to letter D, where it becomes conductive again because the electrons are freely moving and not bound and confined in any directional bonds.